welcome then to this presentation. This is Unit 4 called Further Motion Concepts. This presentation, this unit is only in the separate science GCSE. So if you're doing double awards, you don't need to go through this one. Go straight to what will be Unit 5, but would be Unit 4 for you. If you're doing separate science, stay put. The beauty of this module, or let's have a look in this, some key concepts in here like momentum. We also look at collisions and explosions. We then move on to something called XOVAT, which are equations of motion, and then we look at moments. This unit basically ties up everything we've done so far on mechanics, on motion, but it's quite a useful unit for those of you thinking of doing A-level physics, because this makes up a large chunk of Unit 1 of the AS as well. So yeah, so that's what we've got. Now, again, lots and lots of useful links here. If you're watching this on YouTube, these will all be in the description below. If you're on the presentation, then you obviously can click the links and can follow these YouTube videos of other people explaining this as well. Okay, so on to the first concept. So the first concept I want to cover in this is momentum. Now, we've touched on, when we spoke about Newton's laws, touched on the idea of inertia. And basically, momentum is a way of quantifying it, of giving it a number, giving it a value, of being able to say that this thing has more inertia than this thing. And so, to calculate the momentum of an object, it's its mass multiplied by its velocity. Okay, and it is velocity because direction matters with momentum. Momentum is a vector quantity, so direction here does matter. Okay, now you'll see that it's either given with a plus or a minus sign. Alright, so obviously if we've got the object moving in one direction, we'll give it a plus sign. If it's moving in the other direction, we'll give it a minus sign. As it's the product of mass and velocity, its units are also the product of mass and velocity, so kilograms, meters per second. The symbol for momentum is this funny P sign, a rho, which unfortunately is the same as we use for density, so take care with that. But there we go. Okay, so law of conservation of momentum is as follows. In any collision or explosion, momentum is conserved as long as there are no external forces. Okay, what do we mean by an external force? So this means that a force that's not coming from within the system that we're looking at. Okay, so generally external forces will be things like friction, or could be weight, could be gravity. So if you're talking about a collision and one thing ends up moving upwards, momentum's not going to be conserved there because you've got the external force of gravity, or the weight of the object, as well. What does conserved means? It means that the total momentum before equals the total momentum after. Remember in our rules about combining vectors that if it's in the same direction we add it, if it's in an opposite directions we subtract it. Okay, so let's have a look at collisions then. So in a collision, okay, as long as there are no external forces, the total momentum will be conserved. Key thing with this is that if they're going in opposite directions, which generally in a collision they will be, one will have positive momentum and one will have negative momentum. Okay, and it's important that you use those signs. Now, you might also see the word coalesce. All that means is they join together, and obviously if the objects join together, then you add their masses together. Okay, so if you look at the example that's below me, okay, the red ball has its momentum of 20 kilogram meters per second, the yellow has a momentum of -2, and when they collide, they then have a momentum of 18 meters per second, showing here momentum is conserved because there is no external forces in play. Normally, if we're going to get collision questions, there'll be things that roll, so we can talk about very little friction there, or it could be on ice, that's another one, or on an air trap. All of these things are ways of reducing that friction, reducing that external force. Okay, now explosions. Explosions in physics, all they mean is two objects that are stationary and then move apart from each other. The classic example is a bullet and a gun, or two magnetic poles facing each other that are going to repel. Now, as nothing is moving before we start, the total momentum here must be 0. Okay, so after this explosion, one object will have a positive momentum, one object will have a negative momentum, but they will be basically the same but different. The same but different signs. So here we have a cannonball and a cannon again below me. So before we start, we have 0. Afterwards, the cannonball's moving at 150 meters per second, giving it a momentum of 3,750. The cannon, moving in the opposite direction, is moving at a speed of minus 7.5 meters per second because it's so much heavier than the cannonball. It doesn't move anywhere near as fast, but it still has the same momentum, but negative. And again, you can see total momentum here is conserved. Okay, now we can talk about momentum and Newton's second law. So hopefully you recall that Newton's second law is that it's mass times acceleration. Now if we take the equation for acceleration being change in velocity divided by time, so we put that in, we get force is mass times change in velocity divided by time. If you look, we've got mass times velocity in there now. So we can rearrange this to actually say resultant force is change in momentum divided by time. Now this formula itself is very useful when it comes to talking about the force on an object when it's changing momentum, or the force required to change momentum of an object. When we did car safety in the previous unit, talked about it a little bit there. That basically, as you can see, that time here is on the bottom of this fraction. So that means if we can increase the time, oops, let's draw a slightly better arrow than that. If we can increase the time, then we're going to decrease the force. Okay, and this explains why car crashes, we want to slow an object down as slowly as possible, giving it its greatest time and lowering that resultant force. Okay, now going back to collisions. Now we can classify collisions in two groups, elastic or inelastic. Now an elastic collision, kinetic energy is also conserved. Okay, generally our objects will bounce off each other. So if you look in this example with our red and our yellow, again, if you look at both the total momentum and the total kinetic energy, it's conserved in both examples. However, in an inelastic collision, kinetic energy is converted to other forms. Most likely, elastic potential, heat or sound, is generally one of the objects or both objects will deform. You also can get objects can coalesce, can stick together. So here is coalescing. This is basically the same example we had before. And you can see the kinetic energy has decreased. Some of that kinetic energy would have gone into, probably in this example, elastic potential, deforming the balls so that they stick together. But it could be that, yeah, heat, sound, the common ways that energy is wasted. Okay then, on to XOVAT. Now, if you look at this anywhere else but the WJEC, well, WJEC Physics, not even the WJEC, for maths they change it. This is actually called XOVAT. Like this, we get rid of the X, it's called XOVAT. WJEC basically have kept S for speed to try and make this a little bit less confusing, and have used an X for displacement instead. So these are all vector quantities, and these equations are incredibly useful in most motion, as long as we have constant acceleration. Okay, so we have displacement, x, displacement in meters. We have u, which is the initial velocity. We have v, which is the final velocity. And basically what these mean is initial velocity will be the speed whenever time is 0. And the final velocity will be whatever the speed is when the time is at its maximum value. These are both generally worked out in meters per second, which gives us acceleration a in meters per second squared and time in seconds. Now, these are all, don't worry about learning what these mean. These are all on the data sheet. Now, there are 5 different XOVAT equations. 4 of them are given on the data sheet. The last one that's on this list is not given, so wouldn't be expected to be used. You'd have to do, if you wanted this one, you'd go via other methods. But I've included it here because it's quite straightforward to get, you know, if you look at the other forms of things, if you look at the forms of ones before. And basically the reason we have 5 of them is we have 5 XOVAT variables, so each equation has one thing missing. So our first one, v equals u plus at, there's no displacement in that. So if you are only given final velocity, acceleration and time, you could work out initial velocity using this, well, basically, yeah. So if there's no mention of displacement, you can use that equation. If you're missing acceleration, then you can use x equals a half u plus v over t, which is basically similar idea to speed equals distance over time. If you look at a half u plus v, that's the average speed, and displacement is average speed times time. V squared equals u squared plus 2ax. Here we haven't got time. This equation is quite useful. Those of you who are quite math savvy will realise that this equation, especially if u is 0, v squared equals 2ax, very, very similar to what we did before when it comes to kinetic energy and gravitational potential energy. In fact, that's basically the same maths. X equals ut plus a half at squared. If you're not given v, that's the equation to use here. This equation is one that's used probably the most often out of all the XOVAT equations. So we're given an initial velocity, and we want to work out probably what this is. We're given an initial velocity and we're given an acceleration, and then we're probably given a displacement. We want to work out a time, or we're given a time and we want to work out how far we traveled. This equation is fantastic. We use this the most, really. And then the final one is basically like the previous one, but we haven't got u, which means we're given the final velocity, and we just take away half at squared here. Like I said, don't need to learn these. They are all given, bar the last one, but I wouldn't worry too much about that one. Okay, so using XOVAT. I think the hardest thing students find with XOVAT is just getting started. So for me, I would list what is in the question. So displacement. So I'd write down XOVAT, x, u, v, a, t, and I'd go through the question. So here we're told ball is dropped from rest 5 meters. How fast would it be going when it's hit the floor? And we're told that g is 10. So I list the things down. So I list that I know x is 5, u is 0, v is what we want to know, a is 10, and time we don't know. So I select the equation that only has the things that I either want or have got. I haven't got t, so I select the equation without t. Now, the only thing that can trip you up here is directions. So you have to remember gravity will always act down, and the objects always have 0 vertical speed at the top of the bounce. So if we're talking about a ball bouncing up and it goes up at 3 meters per second, we know that the initial speed is 3, but the final speed is 0. And if we're talking about a speed going up being 3, then we need to make sure we use -10 for the acceleration. It doesn't matter which way you set as positive and negative as long as you are consistent with it. So all the things that are going in the positive direction are positive. All the things that are going in your negative direction are negative. Whoops, I knocked my camera. Okay, now on to a sort of prime example of using momentum and using XOVAT and using energy changes, the ballistic pendulum. Now I've included this as a specific example because it's been on a past paper. Okay, now the ballistic pendulum is basically a way of measuring the speed of a bullet. So you fire it into a target that absorbs the bullet, thus absorbs all the momentum of the bullet, and you make sure it has a large mass so that basically when the bullet hits it, it swings up, but only swings up a small amount and slowly, so that we can easily measure the height the pendulum swings up. Now ultimately, if you're doing this for real, actually what you measure is the angle the pendulum swings at, and you'd use some trigonometry to work out what that gain in height is. But if these ever come up, they won't expect you to do that, so we'll just talk about the height the pendulum swings. Okay, so how we do this? Well, we do this through conservation of momentum, because at least initially momentum is conserved in this case. Okay, so when the bullet enters the pendulum, momentum is conserved because there are no external forces, but kinetic energy won't be, and that energy will go into deforming the pendulum around the bullet, so into elastic potential as the pendulum deforms. Now, where momentum is not conserved is as our pendulum swings up. Okay, why is it not conserved? Because we're going to do work against gravity here. We've got an external force in play. So our kinetic energy of the bullet and the pendulum is being transferred into gravitational potential energy. Now, if you look at the GIF below me, you will see the equations that go through this. So we basically can work out what the change in momentum would be. And from that, we can work out what the speed of our pendulum and bullet would be. And from the speed of the pendulum and bullet, we can work out the height. Obviously, if you're doing this for real, you won't have the speed of the bullet. So you'll probably be working backwards from the height to work out the bullet speed. So there we are, if you want to have a look. Remember, power of a half is a square root. It was just easier to do to a power of a half when I was writing this down. Okay, moments then. Now, so far, all the forces work that you have done is things moving in straight lines. We haven't done anything sort of turning, rotating. Now, moments are forces that cause turning forces. Okay, now the size of the moment depends on two things. The size of the force being applied and the distance from the pivot. Okay, force and distance, they're measured in Newton meters. And you might have seen this if you've ever, things like bikes, you might see on a bike 5 Nm, 5 Newton meters next to a bolt. And that's telling you basically how much the moment, how much the torque, which is just another word for moment, needs to apply to that bolt to get it done up tight. Same in cars, anything basically mechanical, and it's important that you torque the bolts to the right amount, because if they're too loose, then they come apart, and if the torque is too much, then you can end up snapping the bolt or damaging the part. So to work out the moment, it's force times distance from the pivot. And it's important that we remember direction. So here, when we come to directions, we talk about clockwise and we talk about anti-clockwise. rather than up and down or left and right, because we're dealing with things going around in a circle. Now, in any questions that you're dealing with, you will always have an object that's not rotating. So the moments will be balanced. And we call this basically the principle of moments. That basically the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about a point. And that's important. You need to learn that. So if an object is not rotating, okay, and the moments are balanced, then the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about that point. And you'll notice the word sum in there. So if we've got more than one force, then we work out the moment of each one and then add them together. Okay, so if we're applying this principle of moments, then this is how we do it. So first thing I would do is I would always write down the principle of moments. First thing, it's probably going to get you a mark if you don't get anything else. Decide your pivot point. Now, generally, to decide your pivot point, it will be somewhere where there's an unknown force acting. So, could be if it's a seesaw type arrangement, it could be the point where the seesaw is pivoted about. Diving board, again, could be the point where the diving board's held still. Then what you have to do is you have to go through and decide which direction each force is going to make the object rotate. You then calculate the moments for each force separately before you add them together. And you should then have something that you're missing. You rearrange to find whatever's missing. Okay, so over to you. If, remember, you're watching this on PowerPoint, stop the presentation now. Click on the document and it should open up the PDF. If you're watching this on YouTube, the link will be in the description below. Have a go at the questions. When you're ready, restart the presentation or restart the video, and on the next slide will be me going through it. Okay, so hopefully you're watching this having already done the questions. So let's go through the answers. Okay, so we're starting with September, the separate science. All of these will be separate science, the separate science topic only. So we've got Foundation 2018. We've got question 5. So we've got a new tower crane building in the central Cardiff. Okay, and it's a moments question. And they've basically gone, here's a tower crane, and here's a model using moments, and it gives us the equation. Asks us to calculate the anti-clockwise moment of the 2 Newton weight about the pivot in Newton centimeters. So dead easy. This is going to be 2 times 50, which is 100. 1 mark for substitution, 1 mark putting the right answer in. Okay, right. Calculate the distance the weight should be placed. So the moment here is going to be the one we just calculated, divided by the force of that, which is going to give us 40 centimeters. Explain why it would be impossible to balance the 2 Newton weight at the end of the ruler. The 1.5 Newton weight is replaced by a 1.5. Okay, so basically, you've got to remember that 1.5 is less than 2 newtons, so it has to be placed further away which is impossible. Okay, a particular tower crane is capable of lifting a mass of 15,000 kilograms. Calculate the weight of this mass, so we're going to do 15,000 multiplied by 10 to get 150,000 for 2 marks. Nice and simple to get us going. Okay, question 7 then.
Okay, so a velocity time graph below shows the motion of an empty school bus. Use values from the graph to describe the motion of the bus over the time shown. Okay, so what I would do here is I would go through each section talking about what's going on. So from A to B, we have constant acceleration. Okay, and the value then would be 25 divided by 50, which is 0.5 meters seconds to the minus 2. Okay, so from B to C, we have constant velocity of 25 meters seconds to the minus 1. It's also a good idea to say for 80 seconds. Give the time, give as much detail as you can on this. Okay, between C and D, we're going to have deceleration. Now, if we look at this, that line's getting steeper, so we probably could put increasing deceleration. Okay, and we've gone from 25 to 0 in 70 seconds. So we could give the sort of average value of that as well, which is going to be 25 divided by 70, 0.36. As well. Okay, and then we got D to E. So D to E, that would be our average value. Better put that in there. That's the average. Make a note of that. D to E was stationary. And again, put the time in for 40 seconds. And then from E to F, we've got constant acceleration. And we're going to go from 0 to 10. So we've got 10 divided by the time taken to do that, which is 60 seconds. So 0.17 meters per second squared. Okay, and it's that sort of idea. It does say note that no calculations are required as part of your answer, but put them in there. It says use values from the graph, put them in there, work it out. Okay, you can do that, and by doing all of that, you'll get your 6 marks. Okay, use the graph to refer to the graph in the following answers. Calculate the change momentum between A and B. So, change in momentum is going to be mass times change in speed. So that's going to be 10,000 times 25, which is 250,000. 250,000 kilograms meters per second. Calculate the resultant force. So force is going to be change in momentum divided by time. So that's going to be 250,000 divided by 50, which is 5,000 newtons. Calculate the distance travelled between B and C. So that's going to be 25 times the 80 seconds between B and C, which is 2,000 meters. All of these are its 2 marks, one for substitution, one for the right answer. If you get just the right answer, you get both marks. Identical bus travels the same distance, however, it travels at a slower constant speed. State 2 ways that the line on the graph will be different from the one shown. Well, if it's travelling slower, the line would be lower. However, the length of this line would be longer. Yeah, because we've got to cover the same distance, we've got to get the same area. So if it's lower, it's got to be longer. Using the idea of inertia, explain how the acceleration of the bus filled with children would compare to the acceleration of the empty bus. So if we're talking about, we've got to put in here, we'd have more inertia. Okay, so we'd have a slower acceleration. One mark saying more inertia, one mark saying slower acceleration. Okay, so on to 2019. Okay, so let's have a look at this question then. So we have our ice skater. Okay, here's one ice skater with a mass of 50 kilograms, and we've got another one with a mass of 30 kilograms, and it tells us that when they collide together, and then it asks us to work out the total momentum before. So the total momentum before is going to be 50 times 5, take away 30 times 1. Remember, take away, because this is going in the opposite direction, it tells us this is the positive. So that's going to equal 220 kilograms meters per second. Yeah, 250 take away 30 is 220 for 3 marks. After they collide, they come together with a common velocity to the right. Use the equation. So that's going to be 220 divided by their combined masses, which is 80. To give us 2.75 meters per second. Yeah, their masses have come together, so we have to add them up. Okay, then we're on to another moments question. State the principle of moments. The principle of moments says that clockwise moments equals the anti-clockwise moments. So, use an equation for page 2 to calculate the moment, the 2 Newton weight, about the pivot. So we want the moment of the 2 Newton weight, so that's going to be 2 times the distance from the pivot, 2 times 40, which is 80 Newton centimeters. Then it wants us to work out the distance. Well, if they're balanced, the moment's going to equal 80, the force is 5, so the distance is going to be 16 centimeters. Students replace the 2 Newton weight with a 4 Newton weight. Jade suggests that to balance the ruler, they will have to half the distance that the 5 Newton weight is from the pivot. Explain whether you agree with her suggestion. Well, if we go from 2 to 4, that moment will double. So the distance will also double. So basically, she's got it the wrong way around. So she is wrong. Okay, the 2 marks, one for saying that the moment will double, the next mark for that sentence there. You could do it by maths. You could just do that 4 times 40 is 160. So 160 divided by 5 is 32. And again, you basically said double, so she's wrong. Okay, on to the next one then. So now we're on to the higher tier questions. So there's going to be a bit more demand and a bit more effort required on these. So let's get going. Okay, so we've got a timer with shape of a ball dropped. When released, start stop clock. When it hits something, stops the stopwatch. Time taken is displayed on the screen. So the teacher uses the ball for an experiment. He holds it up from the 3rd floor classroom window, releases it, recalls the times. Ball is dropped 5 times during the experiment. So reproducible means that they're collected by different groups. So basically get other people or other groups or students, whoever, to carry out the investigation. And then check if data is similar. Okay, so those are 2 marks there. So you get other people to do it, and then you check if their data is similar. Not the same, won't be exactly the same. They're doing it perhaps slightly differently. But you're looking for similar data. Right, the anomalous result is the one that doesn't fit the pattern. The rest are all about 0.5, and that one's at 1.1. So we use the other 4 to work out the mean. So we're going to add the other 4 up, and we get a value of 6. We divide by the 4 we've got, so the mean time to fall is 1.5 seconds. And does that make sense? Yeah, because we've got that one's 4 below it, that one's 4 above it, 2 below it, 2 above it. So that's smack bang in the middle. Okay, so we use this equation to calculate the drop height of the ball. So x is going to be 0, we dropped it from rest, plus 14.2 divided by 2, multiplied by that mean drop time that we did, like so, and we get a drop height of 10.65 meters. 3 stories, yeah, makes about sense, about 3 and a bit meters a story. Yeah, that's about right. Okay, now this question was the last question on this paper and was a bit of a doozy. So, right, state the law of conservation of momentum. So what that tells us is that the momentum before equals the momentum after. Okay, for 1 mark. The second mark is for saying provided no external forces act, or no external resultant force. Okay, so explain whether this law applies when the block swings up. No, because if it swings up, you've got gravity, you've got weight, so that's an external force. No, because of gravity. In this case, we're ignoring air resistance, it's too low. That's not going to be a problem. Discuss whether kinetic energy is conserved in both stages of the process. Well, if we think about it burrowing in here, we're going to do some work deforming the block. So if we think about stage 1, no as block deforms. And then if we think about that's stage 1. Stage 2, that's also going to be no as some KE, in fact all the KE. So let's just rub this out. As KE becomes potential energy, which we'll get away with calling PE, as block moves up. And in fact, that allows us to do the next part of this question. So it says here we have the mass of the bullet, 16 grams. We've got the mass of the block. The combined bullet and block start to move at velocity v. They move up a height equal to 11.9. Calculate v. So if we think about it, the potential energy is going to equal the kinetic energy. So the kinetic energy is going to be the square root of 2GH. Yeah, multiply both masses cancel, multiply by 2, move the half, and square root it. So that's going to be the square root of 2 times 10 times 11.9 over 100, because you need to work in meters. So the velocity of our block is going to be 2.38 meters per second. Use your answer in part 1 to calculate the velocity of the bullet. Well, in this first part, momentum's conserved, so we can use that. So the momentum of the bullet is going to end up equaling the momentum of the block plus bullet. Okay, momentum before equals momentum after. So we're going to have 16 times 10 to the minus 3, because we want it in kilograms, because the block's in kilograms, makes life easier, times the speed of the bullet equals 2.516, the mass of the block and the bullet, multiplied by the speed that we got in the previous question, 2.38. So U is going to be 2.15 times 2.38 all over 16 times 10 to the minus 3. So the speed of our bullet is going to be I made a mistake on the previous question. Sorry. That's V squared. So V is 1.54. I forgot to square root it, which means that this here is 1.54. And this here is 1.54. So U then is going to be 242.2 meters per second, which makes sense for a bullet. Yeah, 2/3 speed of sound. Yeah, it's only a little bullet. That's fine. Okay, so that brings us to the end of those questions. Well done for making it through. Hopefully that helped, and I'll see you in the next one.
Okay, so well done for making it to the end. Thanks for watching it. I know some of these are pretty long. And like I said, if they help, leave us a comment. If they don't help, leave a comment. If you'd rather the review bits, which make them really long, I'll put in separate videos. Again, let me know. It's not a difficult job to do, and I can put them in separate videos rather than putting them in the main video, and it will make basically 2 shorter videos. Please like, please subscribe, and hopefully they help with your qualifications.